the way to perform like actual eliminations and logic is the update function, and that's where the hard JavaScript stuff begins, because it's a generator function. So for those who are unfamiliar, like this star is not a typo. It means that it's a generator function, and if we look at the life cycle of the regular function, it usually does some calculations, and in the end it returns some result to the one who calls the function. So let's say we have this function. We have this result. Very easy. In case of the generator function, it's basically the function that returns many results as a collection, and you can throw one item of the results from any point of the function lifecycle. So let's define the generator function, and the way to return one item of the results is to use this yield keyword. Hope that I pronounce it correct. I'm not an English speaker. So it's similar to return keyword, but like you return one item of the result and you continue running the function. So you can return many results. You can, I don't know, you can do it in a loop, whatever, and the one who calls the function will get all of them. And you can also use the return keyword in a generator function, but it has different meaning. The return keyword, it doesn't really return something. It just means stop executing this function. Just exit from the function, stop doing anything. So for instance, here we will return 0, then 1, then 2, then we'll return A, which is the first item, then we'll return, and we will not get to returning B or C, like things like that. Let's see it in practice. Like if we just do return in the usual way, see, nothing. We see that result is F suspended. What it means is that it returns what it's called iterator. So this object could be used later to get all result items one by one. and the common usage is just going over them in a loop. But now we didn't have anything because we returned it instead of yielding. So we can change it to that. And let's actually write return here just in case. And now we see that when we go over the results, we have the A and the B, which we did here. And because we returned from the function, we don't have the C. So that's how the generators work. And in case of Sudoku Maker and the update function, what it expects us to return are the changes to the puzzle. So basically, this function again gets called when on each logical step. Like each time it wants to do some elimination, and we could apply some logic based on the puzzle state and perform some candidate eliminations or different things. So, and basically we do it like that. So we can say we want to filter candidates in cells. We want to say that the cells could contain only 1 as a digit. And after we yielded this change, we can continue running the logic and do something else, or we can return, and that's it. So let's go over the example and see what are the types of the things that we can do actually. So the first thing, as we saw, we can remove candidates from cells. Like there are separate methods for that, but they are all similar. Like remove candidates from one cell, remove candidates from multiple cells, remove many candidates from one cell, and so on and so forth, and filter candidates and so like. All similar, and it's easy to understand what it means from the name. What's unusual here is this construction. The format for the candidates is this Sudoku digit set, and the filter candidates in cells. It also accepts an instance of this Sudoku digit set. The easiest way to do it is just to create it from an array. Like you need to guess that. It's like you have auto-completion for that. So for instance, here the template code says that if the first cell has a value, then all cells must be equal to 1. That's a very interesting constraint, I can say. Yeah, so the other things that you could do from the update function, except from removing candidates from certain cells, is you can call the puzzle stop function that basically tells the solver that component is already broken, the puzzle is already broken. So and usually after doing it, there's a return statement to make sure that the function doesn't continue to trying to apply some other logic, like there's no reason to do that, puzzle is already broken. And it optionally accepts an argument with a reason why the puzzle is broken, but you can omit it and it will just say component blah 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 is invalid or something like that, like the puzzle is broken because of this constraint, like it will write the name of the constraint again. Actually, let's read the name here as well, just in case. Another thing that you can do is to remove the current component from the puzzle, and the reason for doing that is basically the components have no state. They cannot remember that they already did some deduction. Each time that Sudoku Maker runs the update function, the component needs to like resolve itself, like do all the deductions from the start. And sometimes the logic is complicated, and it will make the solver slow. So if by some reason we already know that the component always works, no matter what are the other candidates of the cells. For instance, we're implementing the German whispers, and we know that the candidates for this cell is 1 or 2, and candidates from this cell is 8 or 9, which I obviously cannot input right now. So we don't need to know the exact digit, but we know that the component is already fulfilled. So we can tell Sudoku Maker, please remove the current component from the puzzle. It cannot do any other elimination. It did the job. Please continue without that. And another example of what the update function can do is something that is similar but not included in the example, is puzzle replace component, which expects the current component, like which one you want to replace by something else, and one or more, let's do it, one or more other components, usually built-in components. So the reason for doing that is when you already know some digits or candidates on the component, and the component used to be very complicated, but now you know that it's much easier, and you don't need to check it again and again each time when calling the update function. And you just tell the solver, hey, please don't use the current component, please use something that is more simple instead of that. And luckily I will get to this example. Now that we know what we can do inside of the update function, let's actually implement it for the tic-tac-toe. So we have 3 cells here. Let's call them A, B, and C. And we probably need to go over all triples of cells. So the first one is ABC, ACB, BCA. And for each triple, if we know so let's check what are the values. So if 2 cells in a triple have their values, then we probably could apply some logic, right? So if we know that the values are the same, then we know that the third cell in the triple cannot equal to this value. So let's remove candidate from cell. Candidate cell. So let's remove the value from the third cell. And we know that the component already did the job. So let's remove it. And return from the function, so we don't continue checking anything else. On the other side, if we have values in 2 cells, but they are different, then we just know that the component works, and that's it. And I did a boo-boo. Let's see if I left some uncommented code. Oh, yeah, sure. Yeah. Let's check if we have contradictions enabled. No, we don't. So now hopefully the logical solver should tell us that that's not a 1. Yes, it does. So now it can do the basic logical steps, and also the moment you implement the update function, you don't need the validate anymore. Basically, if the update function calls puzzle stop, or if it removes a candidate from cell and the cell remains with no candidates. That's the moment when it understands that the puzzle is already broken. Just make sure that the update function is always tells the solver that the component is broken when it is, like at least when all cells are in, like all cells have the values. Now let's try to check if the brute force solver still works. Yeah, it does. So that's how to code a basic constraint, and let's enable contradictions and go step by step and see if it still does what it needs to do. Yeah. Now it works for a more complicated contradiction step. So for instance, it sees that this cell cannot be a 4 because it will force 2 2s here, and this one will be broken. Some Sudoku. Now it sees that this cell is not a 5, because this one will be 5 by the arrow and will break that. And so on and so forth. Now important moment. The next thing that it's going to do is to input 5 here, and notice what it does to this one. So the logical solver already told that it cannot be a 555 line, and did the job. So we can continue solving the puzzle. Ron Planner asked to try doing anti-tic-tac-toe with entropy groups instead. What would need to be changed? So I don't know actually what exactly it means, but I will assume that it means that for each line like that, we just add an entropy line, right? So again, we have a global constraint. We iterate over all input groups by ourselves. But we need to apply different logic. So we have already prepared the array of cells for each line, and we need something that checks the entropy for us. And the first thing to do is to look if we have standard components for that. And I know actually that we do. It should be group something, different groups component. Yeah, looks like what we need here. So every cell of cells must have a digit from a different group from groups. For instance, if one group is 1 to 3 and one cell has a 1, the other cells cannot be 2 or 3. So it looks like exactly what we need here. Okay, so let's see. I have the answer. Not necessarily, but not 3 of the same strata in a row. No, not 3 of the same strata in a row. I think that's exactly what this component does. Actually, let's check it. A digit from every group from groups must appear at least one in cells or from different groups. Oh, okay, looks like it doesn't do the job. So we need to code it ourselves again. Yeah, let's keep the name the same, but we will have to change the logic. So now, instead of checking the value, we need to check which strata it belongs to, which for the 1 to 6 puzzle would be: first one is 1, 1, 2, second one is 3, 4, and the third one is 5, 6. So let's prepare them in advance. Sudoku digit set from 1, 2. Let's write something that tells us yeah, actually let's use the usual syntax. Let's write a function that tells which strata the cell belongs to. And so let's go over them, and we need to understand how, like, which strata it belongs to. So I didn't do my regular thing, so let's add the objects. Now we have it. Yeah, so let's see what we have on the candidates. Get largest digit, get smallest digit, intersects is prototype of is just from is subs. Oh, is intersects. Yeah, looks like this is the method. So let's say if we want to check that candidates have intersection with the strata digits, so it basically means that it has some digits from the strata. So if we don't have the result yet, then the result is the straighter. Otherwise, we have more than one straighter and we need to return undefined. Something like that looks like. So instead of so instead of getting and comparing the values, we get and compare the straighter. So let's say that we know the straighter for both of them, and if it's the same, then we need to remove all of them. And if they are different, then our job is already done. So let's see. Yeah, look like it works. So let's say now we don't have anything. Let's say we place 1 and 2. And it removes 1 and 2 from here. Yeah, so very similar to what we did before. Just instead of comparing the values of the cells, we analyze which strata the candidates belong to, and also like compare if it's the same one, and if it's the same one, that we don't remove one digit from the third cell, but we remove multiple digits, like we remove all digits of the strata.